brief introduction. Professor in the Department of Mathematics, South Asian University, New Delhi, Professor Kapil Sharma completed his post-graduation from Kurukshetra University and PhD from IIT Kanpur. With his many research publications and 20 years of research, teaching and research experience, his research areas are numerical analysis, singularly perturbed problems, partial differential equations, and functional differential equations. He also received, he actually is the recipient of one very important award, which is postdoctoral award, INRIA France, National Institute for Research in Computer Sciences and Automation, France. So now over to you, sir, for your lecture. Professor Kapil Sharma, now you can start your presentation. Good evening, everyone.
Good evening, ma'am, and thanks for giving a nice introduction.
Sir, you were there with us in recent past for one lecture.
Yeah.
You are a family now.
Deliver a lecture, and it was very, useful interaction.
Yeah.
But if it would be offline, so then things would be the different.
Yeah.
But anyway,
we know, sir. There's a difference between online and offline.
Yeah, we have to survive.
One-to-one interactions, I have some else charm we could have taken. Participants would have been more benefited in that. Anyways, now it's a pandemic period, so we have to work with online.
Sure,
sir. So now you can start. Yeah,
from this pandemic.
Soon. And then we'll again meet you somewhere.
Sure, ma'am. So I think
now you can start.
Yes, ma'am. Sure. So can I share my screen?
Yes, you can share your screen, sir.
Yeah. So share screen. Just a moment. Which file I want to? Yeah, so ma'am, it's visible?
Yes, sir.
Yeah, so I have, I think, 4 lectures. Am I right?
Yes, sir.
So I will try as much as I can cover this lecture. So the basic task which has been assigned to me is to give some enlightenment on the numerical methods for initial value problem. Am I right, Harindri ma'am?
Yes, sir.
Yeah. So I will start with the, I think the participants are new or
Sir, they are teachers working in colleges in Delhi or outside Delhi.
colleges, and also so some part of my lecture will be repeated, which I already given. I hope that there are the audience are new also.
Yes, sir.
So I will start basically my lecture from I mean the beginning, that the numerical evolution of numerical methods for initial value problem. So first we should understand that why we are doing, and we will study these methods in a way that not just a formula, that how these type of method might have evolved that time when they were researched. So it will not only give you a flavor that about these methods, but also give you a flavor that how we should narrow down our problem to do the research. So I will try to convey this in during these I mean lectures. And the main book which would be followed during this these lecture will be by this the very renowned numerical analyst Professor J.D. Lambert, Computational Methods in Ordinary Differential Equation, published by Wiley. So mainly we will cover part from this book. So first I will talk about that. So ma'am, I mean, in this also we have one way delivering, or participant can also interact.
So they can ask questions, and you can take their doubts if they have any.
Okay. If they have some doubts, so they can
put up in the chat box, and you will later on.
Okay, chat box. But I mean, we cannot interact right now. Means suppose I want to ask some question from.
So you can, no issue.
So
You can.
they can respond.
Yes,
Am I right?
Yes.
They can switch on their mic and they can.
Their mic and they can respond.
Okay, good. So in that way, we will start with the numerical. First, I will try to explain that what is a numerical analysis, and then the motivation for that. And basically, I will start from the motivation towards the mathematics, and then why we do the numerical analysis. So first, I will explain what is numerical analysis, and then how this is important. So numerical analysis, analysis is consisted of two components. Number one component is the development of method to find the approximate solution of a mathematical problem or mathematical model. And number two, the analysis of error occurred in the approximation. Am I right? So there are two components. Why it is numerical means we can say that finite numbers and analysis. So it is consist of these two things. In the first one, we are talking about the development of methods to find the approximate solution of a mathematical problem. And the second important component of the numerical analysis is the analysis of error occurred in the approximation. When we talk about the approximate things, so surely there would be some error. So that must be analyzed. So first we will study that why we should do numerical analysis. What is the need of that? So anybody can respond. Yeah, please try to make this a little bit interactive. So if anybody have any, I mean, idea in mind, so please. Okay, so just tell what is a motivation to study mathematics. Anybody can answer, any participant?
Sir, if we are not able to find the exact solution of a problem, then we find the numerical solution or the approximate
Yes,
solution.
approximate. If you cannot solve the any problem, then we find the approximate solution using these methods.
Yeah, very rightly. Yeah, if we don't have any method,
Exact solution.
exact solution, so then we should go for the approximate solution. So first we have to understand that whether this approximate solution or approximate information, is just sufficient for us. First we should justify that, and even before that, whether it's the feasible things or feasible, or I should say that if in most of the situation we are in position to find the exact solution, so then nothing to worry. So then why we should go for the approximate things? Because what is our basic motive to solve a mathematical problem? I think one way is that for the fun we are doing, but that is not the things. In most of the situation, why we solve that? We first convert a real life problem into a mathematical problem. Then rather than solving the our basic motive to answer the real life problem. But to answer the real life problem, there are more than one ways. But the best tool by which we can do a realistic answer, so that is using the mathematics. So using some mathematical concept, we convert a real life problem into a mathematical problem, which we call mathematical model. This thing is clear. Once we have converted that model, then we talk about the well-posedness of the mathematical model or mathematical problem. Once we have done that, so then we can say that either you solve this real life problem or corresponding mathematical problem. So whatever answer you will get from the mathematical problems, you will have the answer to the real life problem. So in that way we do that. So the next thing, once we study the well-posedness means in the sense of hard mark, if you are aware that we say that a mathematical problem is well posed. Number one, it has a solution. Number two, the solution must be unique. Number three, the solution must be stable in the sense that it continuously depending on the
initial values,
on the given data. It's fine. Given data here, the condition is this, and what are the given thing? If we talk about in this platform, y prime is equal to fxy, y x naught is equal to y naught, this f and y0, these are the given data. So then we say that the problem is well posed. So that's I'm just giving you a very toy example. All of you are aware, but I am telling you that how we convert a real life problem into a mathematical problem, and then we will talk about the numerical approximation, and then we come to the in the platform of initial value problem. So now how we do that? For example, I am giving you, I think all of you are being a student of mathematics, so aware about or heard the heat equation. So what is a real life problem? And then I will tell you that how using a mathematics we model this phenomena. So basically our real life problem is that, what is our real life problem? Our real life problem, that suppose we are heating a road, we are heating a thin road. So then what is my real life problem? My real life problem is to measure the temperature of the road at different point and at different time. Because the point which are closer to heat source, so they have more temperature than the point which are of the road which are far from the heat source. Am I right? One thing is this. Another thing, as time passes, the temperature of the road increases. So my task that at different time and different point, I want to measure the temperature of the road. So the one way is that using a thermometer, I can measure that, but it is not realistic. It is not realistic because the road has infinitely many points, and also time direction also you have infinitely many time. Suppose somebody interested at 10 o'clock, 10, 10:01, 10:20, 10:25. So in that way, so it could be, but it is very cumbersome, and in certain situation it's unrealistic. So how we do that? So using some mathematical concept and physics of the problem, we convert this problem into a mathematical model. Now look, suppose let you be the temperature of the road. Being a student of mathematics, so that is a best way. Let us assume that you be the temperature. You be the temperature of the road, or road at the point, because it's a depend on temperature, depend on 2 point, x and t. X is the distance from the heat source and t is the time. So at time x and x comma t, it's fine. So now if we look the physics, what's happening? Basically we are giving we are giving heat with respect to time, and what's happening, and this heat basically diffusing with respect to x. Am I right? Because in the as heat by the heat source, it's going to the road, to the system, and then it is diffusing. Am I right? So we can say that the rate of change of temperature basically is proportional to the diffusion with respect to x. So curly u by curly t is proportional to curly 2u by curly x square, because the diffusion is represented by the second derivative, and rate of the change of temperature is represented by the first derivative. So if I write, I mean denote in the another notation, ut basically is proportional to uxx, and we can say that, if you might have remembered, ut is equal to alpha or cuxx, where alpha is the diffusivity coefficient, which depend on the material of the road and this and that. So in that way, so basically now we have one equation, we constructed one equation, and of course we are interested in the one unknown. But the problem here is that this is not in the unknown. Basically this is in the its derivatives. Am I right? And ut is equal to cuxx. So if you, so now what is a way to get rid of, once you have the derivative, so you want to have the, the unknown. So what is the way? Just integrate that. So once you integrate, so how many parameter would involve in that? Because there is one derivative with respect to time, and another two derivative with respect to space. So in x direction we call space, and t with the time direction. So we generally use this terminology. So in the direction of x, there are two derivative uxx, and in time direction we have one derivative ut. So basically when you integrate, so you have three parameter. And if you just integrate this differential equation, partial differential equation, so you have three.
Excuse me sir, sorry to interrupt.
Yeah, please.
आपका स्क्रीन फ्रीज हो चुका है, शायद वो दिख नहीं रहा पार्टिसिपेंट्स को.
No, but actually now just
You are explaining first.
Yeah, I'm just
Only-
explaining first, because we will start basically the initial value problem. So just this is, I'm giving you the background. So I hope you people are able to follow.
Sir, you are writing somewhere or only explaining?
No, I'm not writing.
Sir, he is explaining only, Chandrasekhar.
I'm
He's
just explaining.
Somebody are asking, sir is writing somewhere. That's why I'm asking.
No. But actually, I wish to write, but it's very difficult. Or I can use the board if anybody want.
Okay,
But,
sir, no problem. No
so,
problem.
are you able to follow me, or should I write, sir?
Sir, you can explain, no problem.
Yeah.
If
So
you are able to write, then okay. Otherwise, no problem. You can explain.
I can try, but it's very. I mean, okay. Just I'm trying. If I would be able to do that, so then it would be very good. Otherwise,
you need multiple
screen. We can do that. Yeah. Again. Yeah. Here. I can use that. Yeah, so basically a problem all of you have understood. So ut is equal to basically, now it's visible, sir?
Yes, sir.
Yes, sir.
Yeah, alpha u x x. So now we, if you talk about once is, so as I told you that first of all we will talk about we have convert. I think all of you are agree that our objective to find this u, once we have assumed that let u be the temperature, temperature of road at the point x comma t, or t comma x, whatever you are taking, x comma t. So it means that basically this was our real life problem was to measure the temperature of the road at the point x comma t. Being a student of mathematics, we have assumed that let u be the temperature of the road at x comma t. Now it's fine. So now our task is to find this u. Am I right? So to find u, we need one, because one unknown is there. So we need one equation. And using the physics of the problem, we have converted this, because I told you that what's happening basically, it's a heat going in the system, in the road, and that is diffusing with respect to x in the system. So ut is proportional to uxx, and we have taken ut is equal to alpha uxx. So alpha, I mean, depend on the material of the road. So now it's fine. But here the problem, what is another problem, that I mean, this relation is not directly in the unknown u, it is in the derivative of u. So once we, I mean, so this thing is clear. Now we can say that rather than solving real life problems, solve this I mean, mathematical problem or mathematical equation. Now we will talk about its well-posedness. So first we will talk about its I mean, existence and uniqueness of the solution. So and then we go for the solution methodology. So when we talk about the solution of this problem, so if we integrate that under certain condition, of course, so when we integrate this problem, when so one thing, if you observe that, so if that this equation is meaningful or not. So for meaningfulness, that u must belongs to C1. C1 means its first derivative with respect to time must be continuous. First thing is this should be, and in the right hand side, that its a second derivative with respect to x must be continuous. So then it belongs to, I mean, we can say that then this problem, this equation has a meaningful, both have the meaning. So now the second thing we talk about its solution. So now when we integrate this, so there will be 3 parameters would be there, with one because of this t derivative, and 2 because of when you integrate with respect to x, so you have 2 from the x. So that's why. So but we have to have a unique solution for the well-posedness of the problem. Uniqueness. So for uniqueness, what we need to have, we need to fix all these 3 parameters. And to fix these 3 parameters, what you need to have, you need to put 3 conditions. Am I right? We need to put 3 restrictions on the solution. Am I right? Suppose I ask you that, okay, go from Akbar Bhavan to Akbar Bhavan, Chanakyapuri to the Connaught Place. So there are, I mean, more than one way would be there. There are more than one way. If I put the restriction that, okay, go via Asoka Road or this and that, so in that way I can fix, I can restrict you to going in a one way. So then I have to put some restrictions. So same thing here. If you observe that there are infinitely many solutions it has, but I am interested to have a unique solution, because suppose we solve this and we say that, okay, the temperature of the road may be this one, maybe this thing, maybe there. So you would be confused. You would be interesting to have a unique way, or one value you want when we I mean model a real life problem to answer that. So in that way we need to put the conditions. So we basically put one condition for the time, and where we put these restrictions, basically boundary of the domain. Am I right? At either at the initially we can do that, because in the when it's going in the domain, so we don't have the control, but initially or at the boundary we can control the situation. So that's why initially we assume, let us assume that initially means when time is 0, or x comma, because I have taken x comma 0 is equal to suppose it's a function of x only, u0 x. So initial temperature profile of the road we know, and the 2 conditions. Suppose the I mean this is x varying from 0 to length of the road is 0 to L. So we can have that at u0 t is equal to say, you can capture the both hand at the freezing 0, and another condition you can put this L comma t is equal to 0. So now look that one this differential equation, and then these 3 conditions will fix, and under these this differential equation, under these 3 conditions, it has a unique solution. So it means that now the problem is well posed. This thing is clear. So now we solve this, and this is known as all of you are aware that this is a heat equation. So whatever solution we are getting, so what type of solution we will get? So our uxt will be uxt will equal to say some function of x and t. Am I right? gxt, where g is a given one. If all of you are aware about the solution, and fortunately for this problem we have the exact solution, but generally it doesn't happen. But fortunately for this we have, and you take any value. Once you found this g, so put any value of x and t, so you will have the answer. Suppose I want to measure this at 0.5. I am taking the value of x is 0.5 and t is 2. So then just put in the formula, and this will be g 0.5 comma 2 will give you the answer, because g is a known function. So you just put the x in place of x 0.5 and in place of t 2, because some combination of x and t would be there. So in that way we will find the answer. So in that way we solve the problem. So any doubt till here?
Sir,
Yes,
there is
sir.
one question.
Yeah,
One
please.
participant asked if the boundary condition are non-homogeneous, the problem will still be well posed.
Yeah, of course it would be well posed. It could be then also well posed in that case. Problem. But our problem, our basic motive here not to study this problem. Our motive just to explain that how we use mathematics to answer the real life problem. You can go and study heat equation, and there are a lot of literature. But of course, if you have some constant term is there, of course, so then it also has a solution. So my basic motive to deliver this is that how we use mathematics to answer the real life problem. So regarding this, any other question is there, or should I move further?
No, sir, no question.
Okay, thank you. So now we are moving to we are coming back that as I told you that fortunately for this particular problem we have a procedure by which we can find the exact solution of a mathematical problem. But I am now making a claim that in most of the situation, the mathematical problem which model real life phenomena are very, very complicated in nature, and we don't have any procedure. We do not have any procedure to find the exact solution of the problem. So then what we should do? Then either we should leave this, but I am saying that most of the, if it could be 1 or 2 or maybe a less number, so then we can leave that, we can explore some other. But I am claiming that in the most of the situation, it is not feasible. Till now we don't have any procedure, or we are not in position to develop a method by which we can find the exact solution. So another thing, okay, rather than finding the exact information or exact solution, so can we find the approximate? Yeah, wherever we are facing the problem, we trying to approximate that, and we will solve the approximate problems. Of course, then in that case we will have the approximate information. So now another, I think, question we should ask, whether this approximate information serve our purpose. I'm making another claim. What is the another claim? Another claim is that in most of the practical situation, the approximate information serve our purpose. Am I right? I'm giving you some example. I think you would be also convinced. For example, in the weather forecasting, suppose in a raining season, I'm planning to go outside. So the information whether it's a raining day or non-raining day, this information is sufficient for me, that how rather compared to how much raining it would be or not, or maybe more precise that whether it would be heavy rain or less rain. This information is sufficient rather than how much it would be exact. Suppose we wish to some policy maker need the I mean prediction for the population, population forecasting after 10 years. 10 years. So rather than the exact population, if it would be, they would be known that approximately this would be the approximation, I mean the population of Delhi after 10 years. So this information is sufficient for a policy maker. Am I right? In financial forecasting, the information that in the near future, whether the market in the upward direction or downward direction, this information is sufficient for an investor. If the market will be in the upward direction, then investor will pour the money in the market. If it is in the downward direction, so then he or she can withdraw the money. Am I right? So I am claiming, so I think in the most of the practical situation, the approximate information is more than sufficient to serve our purpose. So that's why we should go for the approximate method. So that's why I'm telling you that numerical analysis is consisted of two components, and one component is the development of the methods to find the approximate solution of a mathematical problem. Now, okay, so the first component is justified to study. Now, why we should study the second one? Why we should analyze the I mean the error? Because we are saying that at the beginning that in the we will do the approximations. Of course, error would be there, because when we are developing a method, so with the method we should tell that this method has this much error, and now it depends on the user whether this method suits to him or her other or not. I'm giving you one instance for this also, that suppose I wish to predict that from Chandigarh to Delhi, I plan to my journey from Chandigarh to Delhi, and it takes let us assume it's take 5 hours. But if somebody madam says that, okay, I ask madam says that it will take 4.5 or 5.5. So this 4.5 and 5.5, this information is sufficient for me. So here I am tolerating error roughly of order 10 raised to the power minus 1. But there is one instant during the Gulf War, there was a failure of Scud missile of US, and because of that a number of casualties were there, and then they analyzed and they found that there was error of order 10 raised to the power minus 8. So I mean to say that at one instant we are not tolerating of error of order 10 raised to the power minus 8, and on the other side we are able, or we are tolerating the error of order 10 raised to the power minus 1. So that's why suppose we have two methods. One method has the error of order 10 raised to the power minus 4, and other method has error of order 10 raised to the power minus 10. So the if I ask somebody which I should use, so I mean one can say that okay, the best one 10 raised to the power minus 10. But at the same time we know that there is no free lunch. There is no free lunch. Free lunch theorem says there is no free lunch. If you are getting something, so certainly you have to pay for that, in the sense of some other thing. So that's why suppose I want to use that method to to plan my journey. So in that case, I can use that easily. But if I want that, to use that method in simulation of the discus missile, so there I cannot do that. So that's why I will use the method which has the error of order 10 raised to the power minus 12. So that's why whatever error occur in the approximation, that should be analyzed. So this thing is clear, I hope. So now it's you are able to see this screen, y prime is equal to fxy, or still you are seeing the board?
Board, sir, board.
Okay, so I have to stop because now I want to share this one. Stop sharing, I think. Again, I have to share the screen. Yeah. So now we talk about this the initial value problem. Now we talk about the initial value problem. Y prime is equal to fxy and y at x0 is equal to y0. So of course, when I'm saying this is a initial value problem, first derivative is involved here, and with this to get rid of the one parameter, so we have one condition. So now we talk about the well-posedness of this problem, and for that, first we will talk about existence and uniqueness of the solution of this initial value problem. Am I right? So I think all of you are aware about the existence and uniqueness of this problem, initial value problem. Under certain condition on F,
Yes,
on
sir.
F, this problem has a unique solution. So now we come to the solution. So first we will try to find the exact solution of this initial value problem. So anybody can answer what will be the exact solution or of this initial value problem, who did not attend my previous lecture? Yeah, anybody can answer? Yeah, the answer is negate. No, we don't have any procedure by which we can find the exact solution of this. Maybe in certain particular form, particular value of x we can find, but in general we don't have any procedure to find the exact solution of this initial value problem. So I'm just making this claim. For the journal value of f, of course, this f has the sufficient regularity to have the existence and uniqueness of the problem, but still we don't have any procedure which give the exact solution of this initial value problem. So then we should develop the method to find the approximate solution, approximate solution of the initial value problem. So now I need again new sharing. Clear, I think. Clear all drawing. So now here also we will start by assuming let y
Sir,
be
one of the participant asked if
the,
variables, excuse me, sir.
oh yeah, yes ma'am.
Sir, one of the participant asked if variables in fxy can be separated, exact solution can be found.
So that's why ma'am I said that for some particular form of f we can find, but for in general we cannot find.
Okay.
Am I right?
Okay.
Yeah. So
Thank
that's why for some some particular, suppose you take constant, so then you can integrate that easily.
Yes.
Even non-linear function also, f has form y power n. So in that case also we can find the solution for the non-linear one. But of course, if it has a separable form, so in that case, but in general we cannot find. Am I right?
Yes.
Yeah.
Yes.
So now we start, and let y be the solution. Let y be the solution of the initial value problem. The initial value problem 1, 2. Am I right? What does it mean? That y is satisfying 1 as well as 2. So now what is our objective? As in the previous case, now our objective is to find this y which satisfying the differential equation 1 and the initial condition 2. Am I right? So how we start? We start that we will keep y on the left hand side. We will keep y on the left hand side, and we will try to have
सर काइंडली अनम्यूट योरसेल्फ, आप म्यूट हो चुके हैं कपिल सर.
So you're not audible.
Yes.
Okay.
Yeah. Yes. Yeah. So y, we keep y on the left hand side, and where is that? Yeah, here we keep unknown on the left hand side, and we are interesting to have known thing. This is basically y. We can say that y x. Y is a function of what's happening. Where is that? No. Yeah. From here we can take. Yeah, so y on the left hand side, and we are looking something I mean known thing on the right hand side, and we will try to that. So how much time ma'am I have? It's I have to
Another
finish at
10
7.
minutes.
Eh?
Another 10 minutes, sir.
Yeah, so I think I should stop here because or
Okay. The new topic you will take tomorrow.
yeah, because it will take I think 20 minutes more to
Moderators, you
cover. So I'm just giving you exercise. Just try to find out the solution. I'm giving you just the way that
you can take
so
them home.
basically we keep y on the left hand side, and we wish to have on the right hand side the known thing. Known thing. What are the known thing? X. X is the part of the domain that we know, and also we know that y at x naught. So in that term, if we would have the right hand side, so then our work will be over. So in that way, we will try to generate some methods. So this thing is clear. So you should try to do that, and then you will say that wherever you feel some difficulty, so you can take some approximation. So in that way, we will try to generate the different class of methods. So we will discuss. So anybody, if we have 4 minutes remaining, maybe my watch. So please, if anybody have any doubt, till now. Ma'am,
Yes, sir.
so is there any doubt?
I don't think, sir.
No, sir. No, sir.
No, sir.
Okay,
It's
No
okay.
doubt
yes, sir.
from participant
Also,
sides.
we have
Participant said no doubt.
lecture at
You can conclude, sir.
continue at 6 o'clock, 6 to 7.
Yeah, tomorrow at 6 o'clock, you can continue with the same.
Okay,
And you
okay.
have
I
given
will
them the
continue,
exercise, they'll
and
complete in the meantime.
so tomorrow I will give the assignment also.
Yeah.
So okay.
Okay, sir. Thank you so much for your this elaborative presentation, and of course, practical approach of